So we can use some, also we can use some statistic tools like PCA, principal component analysis, for the at the global level for machine learning to reduce the model order. And we could also achieve the model order reduction by on the local level. We can use coarser discretization. And our colleague Antoine, tomorrow he will present his work on the coarsening method for microstructure. And there is some advantage by preserving the locality of the model. By preserving the locality of the model, it could be you could interact locally with the model, and maybe you can do some local update of the model. And now I will introduce our baseline method, numerical coarsening. So numerical coarsening is a local method for model order reduction, and numerical coarsening can decouple the resolution of the material and the resolution of the simulation. Numerical coarsening is a data-driven method, and the state-of-the-art method does not support runtime update of the model. But if we have a topology change in the model, like the incision of the anatomical model, or some material update, like some removal of the material inside the model, it's inevitable to update the model. The data generation and the coarse shape function optimization are two bottlenecks at runtime to update the model. Our method accelerated these two processes and made the runtime update possible. So now we have some basics of numerical coarsening. First, we have a coarse cell, and it can be divided into several phi elements. And in finite element elasticity, the displacement field is interpolated with shape functions in the phi elements. For instance, here it's bilinear shape functions. But in numerical coarsening, the only degree of freedom are the displacement of the coarse nodes in blue. And final displacement are defined by the interpolation of the coarse nodes displacement, like in the equation here. Yeah. And by merging these two equations, we can have the coarse shape function. And to further make the shape function more expressive, this M here doesn't have to be a scalar, it could be a matrix. And I will show now some effect you could have using a matrix shape function. Here is an example to show the expressiveness of the matrix shape function. We have a coarse element, and the blue nodes are the coarse nodes. The green nodes are the phi nodes. When the coarse element is under displacement, if you're using traditional bilinear shape function, it will not show any material behavior and will be mapped as a picture shows here. But if we use a matrix valued shape function, it could be material there. It could have some Poisson effect if we code the Poisson effect into the matrix coefficients. So right now, let us first see the coarse shape function optimization and how we can accelerate it. Here is how we get the matrix coefficients with the baseline method. The baseline method proposed a constraint optimization using a smoothness objective to penalize the gradient of the coarse shape function within the core cell. And the optimization is subject to two groups of constraints. The first group is the geometric constraints. The geometric constraints helps to make the rigid transformation of the coarse element. If you have translation or rotation, it will make sure that the fine nodes follow the translation of the rotation of the coarse nodes. And the data constraints encode the previously sampled representative deformation to the weights. In the smoothness objective, the matrix coefficients with different fine nodes indices are entangled. Therefore, it requires to solve this optimization, it requires to solve a large optimization problem, and it's impossible to run at runtime. And we propose our decoupled optimization here. Still, we use the objective smoothness of the objective, and together with the geometric constraints. But this is just for generating a reference weights, the M2. And after getting the reference weights, we put it in a new objective. And we have another constraint optimization with the geometric constraints and the data constraints. Because of the constraints for each individual fine nodes is independent, and with the Frobenius norm in our new objective, we can decouple the optimization. And the first part of the optimization, you don't involve any data, so it can be done offline. And the second part, you have some data inside the constraints, and you have to do it online. So for each final J, the constraints are independent. And the property of the minimization of the Frobenius norm shows here. It makes sure that you can separate each individual nodes. And now, even with the decoupled optimization, we can achieve an error less than 0.001% compared to the full optimization. And now let's see how we can generate the data. Originally, the data used by the baseline method is generated by deforming the whole object by applying 6 different types of traction on the surface of the object, including 3 types of principal stretch and 3 kinds of shear on pairs of the faces. If the model is huge, the data acquisition on the whole object is either impossible or is very costly. So the baseline method places traction on the whole object. An alternative is to place traction on the local level. You just place a traction on the coarse element, but there is also some problem by directly place the traction on the local elements, because perhaps there is some connection between the regions, between the other regions of the object and the coarse element. So here we propose to put the traction on the oversampling region, which is one ring of the coarse element. And this is a good trade-off between speed and accuracy. To further accelerate the sampling, we use a substructuring strategy. We can see this system as a constraint optimization. You have constraints between each coarse cells. And in this way, we can formulate this problem as a Lagrangian multiplier problem. And factorization of each individual coarse cells can be reused. Furthermore, we found a set of constraints with smaller numbers of constraints and with good accuracy. Here's a timing comparison of our method and single cell sampling and oversampling method. The y-axis is the time in logarithmic scale, and the x-axis is the file elements per number per course element for one dimension. And you can see that the oversampling is much slower than ours, and the single sampling, and our method is just a multiple of single sampling method. Now let me show some demos. In this demo, we can update the model by removing cells within just a half a second. And it's for all the core cells inside the model. And here is some result by comparing the no update one and ours. Also, in this example, we show that we can update the model with topology change. The demo shows a progressive cut of the CT scan. And the model updating time for each cycle of cut costs only 0.2 seconds. In this demo, we show another example demonstrating that we can update the model with material update at runtime. The inner part originally is stiffer, and we will make it softer. And please focus on the no update, the inner part of the no update and ours. The no update one will be much, you will see it will be much steeper afterwards. No update and ours at the original material, it's the same. And if we change the material, you can see ours is much softer at the end. In conclusion, we have made a runtime update of numerical coarsening possible by accelerating the coarse shape function optimization using the decoupled optimization. Also, we accelerated the data generation by limiting the sampling region to one ring over sampling region. And furthermore, we have further accelerated the data generation by reusing the factorization and reducing the number of constraints. And there are some limitations of our work. One of the limitations is that the data of the representative deformation is generated in the undeformed configuration, and it may not be representative in the deformed configuration. If you want to simulate extreme nonlinear materials, this may introduce error. Also, the number of deformation modes are only 6. So this might be not enough. And future work addressing this issue could be interesting. Okay, thanks.
Thanks a lot for the presentation. And so do we have questions in the audience? Yes.
Anyway, I can't hear.
Good, yeah, okay. Oh, great. Yeah, thanks for the presentation. I was really interested in this cutting example that you showed, and I was wondering if you can support non-conforming cuts in your.
It's non-conforming. You cut the coarse element into half, and you have duplicated the coarse element in that sense.
Okay, so it's duplicating. The coarse elements or the fine elements?
The coarse element. The fine element is distributed among the coarse elements.
Right. Okay. Great. Thank you.
Other questions? I had a very naive one. You show an example where you had this stiff center, and then you make it And then you make this center smoother and smoother through
this
you
one.
change it dynamically.
Yeah.
Does it work on the symmetrical case where you have a smooth case and can you make it stiffer and stiffer dynamically? Is it exactly the same thing or not?
I think it's the same thing, but the problem is that it may not be that obvious to see the difference. So you can play the playlist backward, but it may not be that obvious that because you can see that the no update is maybe yeah. I think you can go backwards, but if you make it stiffer and stiffer, it may not be a good demo.
Okay. Fair enough. All right. Then thanks the speaker again.